In this video also we are going to talk about a new objective of the lesson of limits. In this lesson or in this objective we are going to talk about how to evaluate limits numerically. So numerically means we take several values of x when x approaches a number. So let us take this example. If I want to evaluate this limit when x approaches 1, so I have to study the limits from both sides. Let's start with the left side. If I take the limit when x goes to 1 from the left, I have to take values when x goes to 1, values below 1, but they approach 1. And also from the right, I have to take values going closer and closer and closer to 1 from the right, little bit more than 1. For example, here from the left, I take 0.9, 0.99, and 0.999. These numbers are approaching 1 from the left, and their values will be shown later. Also from the right, I have to take 1 point something, so very close to 1, 1.1, closer to 1, 1.01, and closer to 1. Then when I find the values of these numbers, these values we call them numerically. So when I find the first value, it is 6.7, then 6.97.1, then 6.997. So if I can see here clearly that the values of G, or the values after plugging in these numbers, are also approaching a specific number, which is clearly these numbers are going to 7. So in this case, we say the limit from the left equals 7. Let's see what will happen for the limit from the right. When I plug in 1.1 in the function here, so I get what? I get a number. This number is 7.31. When I replace 1.01, I get also 7.0301. I'm moving towards 7 clearly. So also you can say here the limit from the right equals to 7. Since both are equal, as we mentioned before, if the limit from the left equals the limit from the right, so we say the limit exists and equals to 7. So if a function approaches the same value from both directions, from both sides, left and right, we can say the limit exists and equals to 7. Let us take an example. Also here, we have a function and we need to find the limit when x approaches 1. As we mentioned, we take values very close to 1 from the right, bigger than 1, but are going to 1, and less than 1, but they are approaching 1. We don't take very far numbers, we take very close numbers to 1. And when I find their values, I can see clearly here that the results are approaching 3 from both sides, because the left side results 2.3, then 2.7, then 2.9, then 2.99, they are approaching 3 from both sides, which means the limit when x approaches 1 equals 3. One more example is also important. Here we can see clearly I cannot replace -1. So I need to study the limit from the left and the right. And as I mentioned before, we just take values from the left and values from the right. And the results here are very clear, are approaching -2. Now let us take some different examples. Look at this example here. We have absolute value. Before we rewriting the absolute value, let us take some values from the left and values from the right. When I replace -1 directly, I will get something over 0. It does not exist. So I have to take values very close to -1 from the left and values very close to -1 from the right. When I replace them here, we can see also from the left, the numbers are approaching 3. So the limit from the left equals 3. Let me see from the right what will happen. Negative 2.9, negative 0.99, and negative. That means the limit approaches negative 3. Oh, we can see here two different limits. When I get two different limits, the left limit exists, equals 3. The right limit also exists, equals negative 3. But that means the limit when x approaches 1 does not exist, because we have two different heights or two different limits. So we can say the limit does not exist. Let us take the last example here. If I want to find the limit when x approaches 3, first, if I try to replace, I will get 0 in the denominator, which makes some problems in finding the exact limit here. So we need to use another method, which is a numerical method, by taking values very close to 3 from left and right. If I start with the 3 from left, then right, I take numbers very close to 3, which is 2.9, then I go closer to 0.99, then closer to 0.999. And also from the right, I start with any number like 3.1 or 3.2, then I have to go closer, which is 3.01, and very close again, 3.001. When I replace these 2.9 here in the function, we get negative 44.1. When I replace the second number again, we get very big number, which is minus 494. And also when I replace the third number, I get minus 4,994. It means the numbers or the results are not approaching a specific number. They are going clearly to minus infinity. That means the limit in this case is negative infinity. So that means the behavior of this graph is going down to negative infinity. If I go to the right side, when I replace, I get 56.1. When I replace, again, I get 506. When I replace 3.001, I get 5,006, which means the numbers are going very clear to plus infinity, are increasing to plus infinity. It means the behavior of this graph is going up. That means the limit when x approaches 3 from the right is plus infinity. So both sides are infinity and minus infinity. They are not equal. So we can conclude that the limit does not exist, because both do not exist. Both minus infinity and plus infinity. Both are not numbers, so the general limit does not exist. Thank you for watching.